A mind-bending idea. Is reality just an illusion? Have you ever seen a hologram? These fascinating projections are more than just a trick of light. They represent a complex interplay of technology and perception. It's a three-dimensional image that seems to float in space, but it's created by projecting light onto a flat surface. The result is an illusion that our eyes and brains interpret as a solid object. Now imagine that our entire universe, everything we see, touch and experience, is like a giant hologram. This isn't just a whimsical thought experiment, it's a serious scientific hypothesis. That's the mind-blowing idea behind the holographic universe theory. This theory has profound implications for our understanding of reality. This theory suggests that reality as we know it is an illusion, a projection of information encoded on a distant two-dimensional surface. Imagine a vast cosmic canvas where every detail of our universe is meticulously inscribed. Like characters on a TV screen, we exist in three dimensions, but the information that makes us up could be stored on a faraway two-dimensional surface. This analogy helps us grasp the concept, but the reality is even more intricate. It's a concept that challenges our fundamental understanding of the cosmos and our place within it. Imagine a movie screen. The images we see appear to have depth and dimension, yet they are all projected from a flat surface. You see a three-dimensional world with depth and detail, but it's all projected from a flat, two-dimensional surface. This analogy helps us understand how a seemingly three-dimensional universe could be a projection. The holographic universe theory proposes something similar for our reality, suggesting that the information about our three-dimensional universe could be encoded on a distant two-dimensional boundary. This boundary could be at the edge of the universe or even beyond our current understanding of space and time. This idea may sound like something out of science fiction, but it's rooted in cutting-edge theoretical physics. Researchers are exploring the mathematical underpinnings of this theory, seeking evidence that could transform our understanding of the universe. It's a concept that has captivated physicists and lay people alike, sparking debate and pushing the boundaries of our understanding of the universe. As we delve deeper into this theory, we may uncover new layers of reality, challenging our perceptions and expanding our horizons. The implications of the holographic universe theory are vast. If true, it could revolutionize our approach to physics, cosmology, and even philosophy. It invites us to question the very nature of existence and our place within the cosmos. Could there be multiple holographic universes, each with its own set of rules and realities? The possibilities are as boundless as the universe itself. This theory opens up a realm of speculation and wonder, urging us to explore the unknown. Ultimately, the holographic universe theory challenges us to rethink our understanding of reality. It suggests that what we perceive as solid and tangible may be nothing more than a sophisticated illusion, a projection of deeper truths encoded in the fabric of the cosmos. As we continue to explore this mind-bending idea, we may find that the true nature of reality is far more complex and wondrous than we ever imagined. The journey to uncover these mysteries is just beginning, and the answers may lie in the stars.
To grasp the holographic universe theory, it helps to understand how holograms work. Holograms are fascinating because they encode three-dimensional information on a two-dimensional surface, creating an illusion of depth and volume. A hologram is created by recording the interference pattern of two laser beams on a photographic plate. One beam, called the reference beam, illuminates the plate directly, while the other beam, known as the object beam, reflects off the object being recorded. When illuminated correctly, this pattern recreates a three-dimensional image of the original object. The light waves interfere with each other, reconstructing the light field that originally came from the object. The key is that the entire information about the three-dimensional object is encoded on the two-dimensional surface of the hologram. This means that every part of the hologram contains information about the whole object. Even if you cut a hologram in half, each piece can still project a complete image, albeit with a smaller field of view. This property is known as redundancy, and it highlights the robustness of holographic data storage. This ability to store information about a higher dimensional object on a lower dimensional surface is central to the holographic universe theory. It suggests that our universe might function in a similar way, with all the information about our three-dimensional reality encoded on a two-dimensional boundary. Think about a regular photograph. It captures a moment in time, but only in two dimensions. It captures a two-dimensional representation of a scene. You can see the height and width, but not the depth. Now imagine a hologram of the same scene. Unlike a photograph, a hologram contains information about the depth and position of every object, allowing you to view the scene from different angles and perceive its three-dimensionality. It contains information about the depth and position of every object, allowing you to view the scene from different angles and perceive its three-dimensionality. This multi-angle view is what makes holograms so unique and powerful. This remarkable property of holograms, where information about a higher dimension is encoded on a lower dimension, forms the basis of the holographic universe theory. It proposes that our universe might be a projection, much like a hologram, suggesting that our three-dimensional reality might be a holographic projection from a two-dimensional surface. This idea challenges our understanding of space and reality, opening up new possibilities for how we perceive the universe.
The seeds of the holographic universe theory were sown in the study of black holes. These enigmatic entities have fascinated scientists for decades, serving as cosmic laboratories for testing the limits of our understanding of the universe. These cosmic monsters are regions of space-time where gravity is so strong that nothing, not even light, can escape. The immense gravitational pull of black holes warps space-time itself, creating a region from which there is no return, known as the event horizon. In the 1970s, physicist Stephen Hawking showed that black holes emit radiation, a phenomenon now known as Hawking radiation. This groundbreaking discovery challenged the previously held notion that black holes were completely black and could only absorb matter and energy. This discovery led to a paradox. According to quantum mechanics, information cannot be destroyed. The laws of quantum mechanics dictate that the information about the state of a system must always be preserved, even if the system undergoes drastic changes. However, as black holes evaporate through Hawking radiation, they seem to erase the information about the objects that fell into them. This apparent contradiction between the behavior of black holes and the principles of quantum mechanics posed a significant challenge to our understanding of the universe. This puzzle, known as the black hole information paradox, baffled physicists for decades. The paradox suggested that either our understanding of black holes was incomplete, or the fundamental principles of quantum mechanics needed to be revised. Imagine throwing a book into a black hole. The book contains information. The pages, the ink, the words, all represent a specific arrangement of matter and energy. According to Hawking's calculations, the black hole eventually evaporates, seemingly destroying the book and the information it contained. This process, if true, would mean that the information encoded in the book is lost forever, violating the principles of quantum mechanics. This apparent loss of information contradicted the laws of quantum mechanics, creating a significant puzzle for physicists. The black hole information paradox forced scientists to reconsider the relationship between gravity and quantum mechanics. This paradox suggested that our understanding of black holes, and perhaps even reality itself, was incomplete. It hinted at the possibility that there might be a deeper, underlying theory that could reconcile the principles of quantum mechanics with the behavior of black holes. It hinted at a deep connection between gravity, quantum mechanics, and the nature of information, paving the way for the development of the holographic universe theory. This theory proposes that the entire universe can be described as a two-dimensional information structure painted on the cosmological horizon, challenging our conventional notions of space and reality.
Section 4. The holographic principle emerges. Rethinking reality's fabric. In the mid-1990s, physicists Gerard T. Hooft and Leonard Susskind proposed a radical solution to the black hole information paradox. They suggested that the information about everything that falls into a black hole is not lost, but is instead encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea, known as the holographic principle, states that the information content of a region of space is proportional to its surface area, not its volume. It's as if the universe is a hologram, with all its information projected from a distant boundary. The holographic principle emerged from the study of black holes and their puzzling characteristics. Think of a can of soup. You might think the soup's information is contained within the can's volume. However, the holographic principle suggests that the information could be encoded on the can's surface, like a label describing the contents. This principle, though initially applied to black holes, suggested a profound possibility. Could our entire universe be a holographic projection from a distant boundary?
Section 5, From Black Holes to the Universe, a Cosmic Hologram. The holographic principle, initially proposed for black holes, had profound implications for the entire universe. If the information about a black hole is encoded on its event horizon, could it be that the information about our universe is encoded on a distant cosmological horizon? This is the central tenet of the holographic universe theory. It suggests that our three-dimensional universe is a holographic projection of information encoded on a distant two-dimensional surface, much like the hologram projecting a three-dimensional image from a two-dimensional plate. Imagine our universe as a giant sphere. The holographic universe theory suggests that everything inside this sphere, all the stars, galaxies, and even ourselves, might be a holographic projection from information encoded on the sphere's surface. This mind-boggling concept challenges our intuitive understanding of reality, suggesting that our perception of a three-dimensional universe might be an elaborate illusion.